My name is Ziwen from our Scout Research Group at UC Irvine. And today I will present our work titled Too Afraid to Drive: Systematic Discovery of Semantic DOS Vulnerability in Autonomous Driving Planning on the Physical World Attack. This is joint work from our group and also our collaborators at UCI and UCLA. So nowadays, the high-level autonomous driving vehicles are publicly on the road. So those vehicles can drive automatically even without the human interaction in most cases. Some companies like Waymo, Baidu Apollo, GM Cruise are already providing public service even without the safety drivers. Now, I will first revisit the existing security works in this area. So the first necessary steps in AD system is called sensing. So in this step, the vehicle will understand the surrounding environments by using different sensor data. Some common components in this step include camera object detection, LiDAR object detection, and also there's multiple sensor fusion, which will combine the different sensor inputs. And also there's prediction, which will generate the prediction trajectories for surrounding objects. And there's also localization, which can tell the position of the vehicle by using different sensor data. But unfortunately, previous work have already demonstrated that most of the components here are vulnerable to external attackers at a certain extent. So however, there are more steps in AD system, so such as planning, which will generate the concrete driving trajectories for the vehicle. And also there's control command, which will transform the driving trajectories into the concrete control commands and give it to the real AD vehicle. So natural question comes here. So can we think about one more step ahead from the security perspective? So will the next step, the planning or the critical decision making in autonomous driving, also vulnerable and also exploitable to the external attackers? So to answer this question, let me first introduce our definition of vulnerability here. So we define a type of vulnerability called semantic vulnerability in AD planning. So that means some vulnerabilities that can be exploited by the external attackers and also leads to unexpected driving decisions. So let me illustrate this more. So here's the AD system, and there's sensing and planning steps. Now imagine there's an external attacker, and the attacker could find a way to manipulate the system inputs of the whole AD system. And those inputs will be propagated into the planning, and thus triggers some bugs or design flaws inside such system. And furthermore, those bugs and design flaws will lead to some unexpected driving decisions. And one type of such decisions could be overly conservative one, such as sharp stopping, permanent stopping, or giving up driving critical decisions, such as lane changing. And we focus on this type of vulnerability because we hypothesize that this is more generally exposed to today's AD system. And also in our work, we refer to them as semantic DOS vulnerability because they literally disrupt the service that could be provided by the AD vehicles. And now, I will introduce more about our problem formulation. So our next step is what are the target of our attack? So actually, we are thinking about the behavior planning. So what is it? Let me first open the box of the planning system. So usually in the planning system, there are 3 sub-steps. So the first step is called route planning. In this step, it will generate the road segments for the vehicle to follow. And the next step is called behavior planning. In this step, the high-level driving decisions will be made, such as collision avoidance or the lane changing. And also the next step is called local planning. So this step will transform the high-level driving decisions into the concrete driving trajectories. And our focus is the second one, because our target is to find those unexpected decisions. And next, I will also introduce the threat model of our work. So how could the attacker manipulate the external inputs of the whole AD systems? Actually, our answer is very straightforward. The attacker could simply use some common roadside objects, such as a dumped cardboard box or parked bicycles. So those objects are pretty common in the real world life, and also thus make our attack very practical and stealthy. So, and the last piece of this problem formulation is the consequence. So what can the attacker do if he can trigger those overly conservative behavior? So the first consequence is the bad user experience. So imagine that the vehicle is providing some robo-taxi or delivery service, and it gets stuck in the middle. So it can definitely damage the user experience. And also there's possible safety concerns. Imagine that the vehicle is driving on the highway and it suddenly makes a sharp stop decision. And actually, this will be demonstrated later. And also, there's block public traffic. And this can be more severe if it happens in some sensitive area, such as in front of the fire station it can actually lead to law violations. And now, before jumping into what we have done, let me first show you a demo we have created based on a semantic DOS vulnerability we discovered in Outwell.ai. And Outwell.ai is actually a full-stack open-source AD system. So this picture is a scenario setup, basically our attack scenario setup. And so I'll say for the most of human drivers, if you found this as a heavy off-ramp, you will probably just ignore them or slightly slow down. Because this setup is actually pretty common. So let's check out these two pictures I took around our campus. And also, since this is highway off-ramp, so unexpected stop could definitely be dangerous. And now let's see how the Outwell will react to this. And here's our attack scenario setup. And you can see in the simulator, this is highway off-ramp, and we put two common roadside objects, which are completely off the lane. And let's see how the Outwell will react to this. Now it's normally driving. And we can see it make a sharp brake and a permanent stop in front of the off-lane objects. And now let's see the possible safety consequence we have demonstrated that. So imagine that there's a human-driven vehicle following the AD vehicle. And we can see that this rear-end collision may happen due to this unexpected stop when the lane is totally empty. And now I will jump into basically our designs. I'll jump into the root cause of this case. So how could this happen? So in the AD planning decision logic, so when the vehicle is driving inside the lane, and now let's see the car width is 2.11 meter, and also the road width is 3.5 meter. So in the normal case, this vehicle can definitely safely drive inside this lane. So when there are some static objects around, the planning decision logic will try to add some lateral safety buffers. So in the Outwell's case, the safety buffer is 1.2 meters. And in this case, after applying the two lateral safety buffers, the remaining space will become the drivable space. However, in this case, the drivable space could be as small as the lane width minus twice of the lateral safety buffer, which is much smaller than the car width. In this case, the AD vehicle will think it is not safe to parse those two static objects, even though it is off the lane and the lane is totally empty. And you can see we demonstrate this. It will have a permanent stop inside the simulator. And now I will introduce what we have done to discover those vulnerabilities. So we have designed a tool named PlanFast, which is a novel dynamic testing tool that can automate discover those semantic DOS vulnerability. So however, building such a tool is not straightforward. So in this page, I'm going to show you some challenges we have met. So we just follow the normal fuzzing techniques. So first, we have an input generator, which will execute the inputs of planning. And next, we also have some input generator, which can generate inputs and give it to the executor. And besides, we also have a seed selection, which can determine which input is better in terms of vulnerability discovery. And those three components can form an evolutionary testing loop. And the first challenge we met here is how can we determine which decision is an overly conservative one? So this actually means we have to design some domain-specific testing oracle. And besides, we also have the second challenge here is we have to give some constraints on the input generation. So for example, you cannot arbitrarily generate a vehicle that completely blocks the road or put it in front of the vehicle. So this test case actually does not make any sense for our design. And the third challenge is that we need to design an efficient feedback that can boost the whole testing process. And now I will talk about our solutions here. So our first solution is called planning invariant. So basically, this is our domain-specific testing oracle. So we design it as follows. So under a specific planning scenario, no matter how the attacker controllable objects change, the desired planning decision should always be the same. Now let me demonstrate it with a simple example. So in the common lane following case, usually no matter how the attacker puts the static objects there, the vehicle should normally drive inside the lane. And that's actually our definition of planning invariance. However, under some specific case, if the attacker could find some specific placement of static objects, and that leads to a stop decision of the vehicle, then that is actually a violation of our planning invariance. And that actually means a discovery of semantic DOS vulnerability. And we can also formally express this with temporal logic. And also in our work, we have systematically defined those planning invariants under 8 diverse scenarios. And we also give some constraints to the moving pedestrians and also vehicles. And based on this, we can build a test vulnerability checker based on this definition of planned invariants. And next, I will talk about our input generators. So to solve the challenge 2, we actually built a 3-step input generation strategy. So in the first step, we will generate static properties for each object, such as the velocity, position, or the heading. And on the next step, we will try to enforce them to satisfy the constraints we have here. And in the third step, we will give some dynamic properties, such as the moving trajectories for the moving pedestrian and vehicles. So by doing that, we can generate the inputs that satisfy all the domain-specific constraints and also maintain the diversity and inheritance during mutation. And our third solution is a specific matrix that can guide the whole testing process. We call it BP vulnerability distance. So this is a gray box distance. So because our idea is we want to trigger some unexpected decisions. So that means reaching at some specific line for code in the source code. So our idea is very straightforward. So we want to extract all the decision-related predicates and use the distance between the operands to guide the whole testing. However, building such a tool is not that straightforward in the real-world program. For example, this is a control flow graph in Apollo, very small part of it. So to address that, we have an offline static analysis plus the online dynamic testing process. And now let's merge all the designs together. So on the left side, you can see we have the offline analysis phase. In which, given the source code, we will generate the control and data dependency and then instrument the binary. So that in the online testing phase, we can have all the instrument binary, which can generate the vulnerability distance we want to use. And next, I will talk about the evaluation. So we have applied the plan files on 3 different implementations of BP, and we are able to successfully discover 9 previously unknown semantic DOS vulnerabilities. So one of them is caused by some program implementation problem, and the others are caused by overly conservative design, such as planning parameters, or the overly conservative estimation of object moving intentions. And also, we have tested on diverse driving scenarios, including lane following, lane changing, lane borrowing, and also different type of intersection passing. And next, I want to show you a few exploration case studies we have created. So the first one is we have demonstrated the previous vulnerability I showed you in the demo in the real-world driving trace. So we use a VD vehicle to collect the driving trace, and you can see by just applying to static objects, we can trigger a stop decision in front of those objects. And we also have a stop sign scenario demonstration. So the attacker could simply use some parked bicycles around the intersection, and this can lead to a permanent stop in front of a stop line. And we also have a lane changing scenario where the attacker could just use a tailgating vehicle to force the AD victim vehicle give up a lane changing decision. And next, I'll talk about the conclusion. So basically, we are the first to perform AD planning specific vulnerability discovery. And we use a domain-specific problem formulation and with a practical threat model. So we have designed a tool, and we are able to successfully discover 9 previously unknown vulnerabilities. And we also have a few exploration case studies. And what's more, we have informed 24 companies which are currently developing AD software. And that's the end of my presentation. And now I'm happy to take any questions. Thank you.